Okay, so we were talking about these three questions, and a lot of rigorous work has been done on proving the robustness of bounds. And I think like one question which would be in some of you might be thinking is what happens to inflation actually? Like, does quantum gravity resolve the problems of inflation? And this is where like a lot of work has been done, and I'm sorry to condense it just in one talk. And one of the very nice things which we proved, which we showed, but we unfortunately never uh, published it, was that the quantum gravity does resolve the past singularity in inflation. And this was done in 2008, 2009 itself, in which you can see that if you take an inflaton and if you plot the volume of the universe versus an inflaton, and you can look at the time span or the volume span that this simulation is covering, that the inflaton starts from somewhere on the top, rolls down, will have a reheating and so on. And if you go backwards towards the Big Bang, in the standard inflationary model, this will go into the Big Bang. But what we showed was that there is actually a bounce, and then it latches on to a deflating universe on the other side. And this is where one can do actually the quantum simulations in this particular regime to show there is a bounce. Then using effective dynamics, a lot of things were done. First, it was shown that loop quantum gravity effects lead to attractors in the theory. Like if you start from a bounce for arbitrary potentials, then after the bounce, there is inflation is very generic. Inflation is very naturally there. The probability of inflation to occur is extremely high, as was shown by Ashtekar and Sloan and Korichi and Karami, thanks to these attractors which naturally form after the bounce. And also, a very interesting work was done by Bhardwaj and Copeland, who is one of the top cosmologists, inflationary cosmologists, and Guillermo Loco, in which they showed that there can be different kinds of bounces. This was already understood, kinetic dominated bounces and potential dominated bounces. But for the Starobinsky inflation, which is right now one of the most favored models of inflation, there can be only a kinetic dominated bounce. And if you have a potential dominated bounce, then Starobinsky inflation will be not so much compatible with the bounce. Okay. Now there was a question, what happens to highly quantum states? And this question was answered both in the analytical side as well as the numerical side. And you can see like this is a simulation here, which has very, it's not Gaussian at all, it's highly quantum. And there was a debate going on sometime in 2010, 2012, so on, that these fluctuations will completely destroy the bounce. And you can see like these states, this state just completely very nicely bounces again from a minimum volume. And actually what is happening is if you plot the bounce density versus the squeezeness of the state, if you're plotting a squeeze state, then you find that more squeeze the state, if you increase the squeezeness of the state, actually the bounce density is going down instead of going higher. So what it means is that the more quantum the state is, those H bar effects now in the state are actually happening, the GH bar effects in the quantum difference equation, not canceling them, but adding on them to cause a bounce much, much earlier. So quantum fluctuations were found to lower the curvature scale at which the bounce occurs, and the fluctuation in the state actually enhance the repulsive nature of the gravity. Then this is an example from the anisotropic spacetimes, because you can ask this question, well, this was all for the isotropic spacetimes, that's fine, but anisotropic spacetimes, what happens? And this is an example for a Bianchi 1 vacuum model in which the Madrid group did an earlier work. But this is computationally a very challenging exercise. The moment you go from a one-dimensional gravitational degree of freedom to more than one-dimensional, computationally it just becomes, it just exponentially increases, that all those computational expenses. And this plot was generated through in LSU, this collaboration with the numerical relativist Peter Diener and one of my past students, Anton Joe, and another numerical relativist, Miguel Migavan, who was my postdoc, in which we developed these numerical loop quantum cosmology techniques, in which now we are plotting is the universe in two directions. One scale factor, this is the Bianchi 1 vacuum spacetime, has three directions, and what we are plotting is one direction versus the other one. And you can see that there is actually a bounce. If this was and this black curve is an effective dynamics curve, which again matches beautifully with the quantum expectation values. If this was classical theory, this would have gone into a Big Bang or Big Crunch. One also finds that an isotropic shear remains bounded throughout the evolution, and the effective description turns out to be a beautiful approximation in the anisotropic models. That is why you can believe in effective description so much and then use it for phenomenological purposes. You don't have to go back, once you take a new model, you don't have to go back to the drawing board and then rework every detail of numerical simulation in effective description. You can just probably assume the effective description, state the caveat I'm using effective description, and go ahead with the phenomenological predictions. Now I'll briefly talk about the modifications of standard loop quantum cosmology which have appeared recently, thanks to this forgotten work earlier of Yang Ding and Yongge Ma in 2009, which was rediscovered from very different ways. That Hamiltonian was rediscovered by Dapper and Klaus Ligner, and then with my collaborators Baofi Li and Ansong Wang, and the collaboration between Erlangen and Warsaw groups, this work was redone. The main idea is that in the standard loop quantum cosmology, we have started with a Hamiltonian constraint, which are the Euclidean term and the Lorentzian term, which actually look like this. And this led to this Arsteger-Boerwald-Lewandowski quantization on which the APS model and everything else was based. But you could have done something different, and this is what was in the Yongge Ma and his students showed, that you could have quantized these Euclidean and Lorentzian terms differently, as is generally the strategy in loop quantum gravity. In Arsteger-Boerwald-Lewandowski paper, these were combined earlier because you were dealing with the homogeneous space-time, and then they can be related in the isotropic setting. You can combine them and then quantize them. What Yongge Ma and his students showed was that, let us say you do not combine them, but you quantize them separately, then they found that the Hamiltonian constraint looks different. And there are essentially two ambiguities which emerge. There is one, the quantization of how do you do the Lorentzian part, and this leads to what is called as modified loop quantum cosmology version 1, which is now called as MLQC1. But one can also use, instead of Arsteger connection, one can use the extrinsic curvature because the intrinsic curvature is 0, and then quantize, and then this results in MLQC2. So MLQC1 appears if you just quantize them separately, as one would do in a more non-simpler model than loop quantum cosmology. And MLQC2 appears if you don't use Arsteger connection, but if you use the extrinsic curvature. Now, if you do that, then the physics of bounds changes. And this leads to non-trivial modifications of Friedmann dynamics. The Friedmann dynamics changes, and that has been studied in detail in the last few years. So the red curve here, what you see is the bounds, volume versus time of loop quantum cosmology for a massless scalar field, perfectly symmetrical bounds. The green curve, which you see, is MLQC2, again, a perfectly symmetrical bounds. But the quantum difference equation is now fourth order. It's not second order. And what you see as the blue curve is MLQC1, in which the bounds is not symmetric, even if you have a massless scalar field. Actually, what happens is that before the bounds, the universe is going into a exponential deflation in a sense. And there is an emergent cosmological constant with a very high Planckian magnitude, which appears naturally from the theory, which is dictating this blue curve. So if the question is, are all bounces in loop cosmology always symmetric, even if you take massless scalar field? The answer is no. If you take MLQC1, which is one of the very natural ways to do loop quantum cosmology, if you are coming from the cosmological sector of loop quantum gravity, then it will be a non-symmetric bounds, very non-symmetric bounds. Later on, it will look similar. So one of the things which we understood in last few years was, do they always look similar? Like, why are we even concerned about what happens pre-bounds? Why not, if in the post-bounds, they are all looking very similar, so maybe the physics is very similar. I think like this answer is wrong, and we have shown that. It depends on the kind of matter or potential you're taking. And what we showed is that for MLQC1, actually, there cannot be any cyclic models, like what I showed for you for the cyclic models of loop quantum cosmology. With my postdoc, Baofi Li, a few years ago, we showed that in loop quantum cosmology, you can have cyclic, if you take a potential which allows a cyclic model, that's possible. But in MLQC1, actually, it's very difficult to get a large macroscopic universe coming through cyclic models. So cyclic models are actually forbidden if you look at this MLQC1. And I think that's a very cool prediction, because cyclic models themselves, if you look at the ekpyrotic models of cyclic models, they are themselves in observational constraints. a lot of tight observational constraints. And in some sense, this is just coming from the theory that perhaps loop quantum gravity is guiding us more towards inflation rather than saying that the universe went through cycles and so on. But again, these are all toy models, just 3 toy models. Perhaps you can construct your own new loop quantum cosmology and study the models. Like my goal was just to answer the robustness question here, that what happens if you take different models and so on. Then this question was asked whether loop quantum cosmology resolves all the singularities. Interesting thing is that even though I showed you that energy density is bounded, it turns out that space-time curvature invariance can in principle diverge for some space-times in loop quantum gravity. And what you can see is that if you take a spatially flat isotropic universe, then the expression for the Ricci scalar looks like this. But then depending on the equation of state, it is possible that even if energy density is bounded, then the divergence of the equation of state, which can just occur because of the divergence of pressure, can cause the space-time curvature to be unbounded. And this is not some very, very exotic model. Like famous cosmologists like John Barrow and so on have spent a lot of time on studying these highly exotic equations of state because they are good fits to dark energy models and so on. So the idea is that yes, in loop quantum cosmology, Ricci scalar can indeed diverge. And when we first discovered it, I was very nervous because I thought that, well, there goes any possibility of getting any permanent position probably, because whatever I've done in the postdoc period is probably out. But it turns out that if you look at it carefully, and if you look at the energy conditions, the strong energy condition and the weak energy condition, it turns out that the strong energy condition is actually satisfied. Even if you have the space-time curvature which diverges, one can show that that singularity is physically irrelevant. Because what is the question? The question is, even if the space-time curvature diverges, when is the singularity physically relevant? And one can actually show there are these strong condition and weak conditions. The singularity at some affine parameter is strong and physically relevant if this integral diverges, otherwise it is weak. One can actually show that for all the events where the space-time curvature actually diverges, all those singularities are weak singularities. And when the space-time curvature and the space-time, all the strong curvature singularities are actually resolved. And this is even true in the versions MLQC1 and MLQC2, which we have recently found. Even in those ones, one has done this analysis of strong and weak curvature singularities. Even there, the space-time curvature can diverge. But we have shown that in all events where the space-time curvature diverges, it's a weak singularity. Weak singularity also means that the geodesics can be extended beyond those events. These also mean that you can construct sufficiently strong detectors which will not be destroyed. So the main message is, yes, the space-time curvature can diverge, but those are weak singularities and strong curvature singularities are always resolved. So this is now the summary of part A. In the summary, I would just say that loop quantum cosmology has, in what we have shown you right now, it provides a glimpse of the origin of the universe using the non-perturbative quantum gravity methods. The emerging picture from simple models. I will still say simple because we haven't shown that with full rigor using inhomogeneities. So I'm stating with the caveat. Simple but still very non-trivial models is that the Big Bang is not the beginning and Big Crunch is not the end. And singularity resolution has been achieved in various isotropic and anisotropic models by various groups. And I'm sorry if I failed to mention some of the literature. There is no need to introduce any exotic matter, ad hoc assumptions, or fine-tuning. Now in literature, you would see singularities are resolved if you go beyond loop quantum gravity. But you would always see either there is an exotic matter, there is an ad hoc assumption on the wave function at the Big Bang, or there is a fine-tuning. The existence of bounds has been tested for extreme conditions using high-performance computing. Bounds occurs for states in dense subspace of the physical Hilbert space, at least for one particular model. The discreteness of quantum geometry bounds the energy density. It binds in an anisotropic shear and curvature scalars, unless there you assume very exotic equation of state. Yes, some Ricci scalar or like Crashman scalar can blow up, but that is a weak singularity. Geodesics can be extended. We have proved that. The main open question, and this ties to the slides I was showing earlier, is singularity resolution, which I've shown you so far, is an artifact of symmetry-reduced models? Or are we in the same historical analog of where perhaps Rai Chaudhuri was at some point before the singularity theorems were being developed? Is there a non-singularity theorem from loop quantum gravity, which all these results are precursor of? That yes, the singularities can be resolved, and probably like some of the young audience here can be motivated enough to see these results, to take them forward, and perhaps take it as an ambition that maybe one day we'll have a non-singularity theorem from loop quantum gravity. Okay, I think I will pause here, Jurek, for some questions.
Param, so you asked me to tell you when you have been speaking for 15 minutes. So I think it's more or less 15 or 16 minutes already have passed. Other questions? Yeah. Okay. But please make it short. And Param, also make your answer as short as possible.
You're saying before that the inflation is very much probable to happen after the post-bonds event. Is this inflationary things as a seed of a quantum gravity effect, or should we add some additional matter for it to be happen?
That's a very good question. So in all of these slides and the slides which are going to come, inflation is put in by hand. We are only quantizing the gravitational part, and we are treating the matter part not as in the loop quantum gravity way. And we are importing that potential phenomenologically. That's what we are doing. So, Jurek, this was the short answer.
Thank you.
Thank you. Let us go on.
Okay, so now I would like to go to the second part of my talk, and I'm actually still at slide 44, and I'm not sure like how much to cover and how much to speed up, but I want to cover this part because this is if you want to jump into loop quantum cosmology or loop cosmologies, and if you want to see like which are the ways like you can try to probably make the new contributions, novel things, then this is one very good trajectory for students. And the idea is Hamiltonian framework for cosmological perturbations and how to explore quantum geometric effects in CMP. And why I'm focusing on this in slightly more dense ways, because I also learned it with a lot of effort along with my postdoc in last few years. And I thought like maybe if I can communicate the main steps, that will be very useful for everyone. The useful references for this part B are, I think, like this for the first paper by David Langlois in 1994. This forms the backbone of one of the main approaches by Agulo, Ashtekar, and Nelson, on which gave this one of the first approaches, which is called the dress metric approach. Also a very closely related approach by the Madrid group, which is called the hybrid approach. And then I'm pointing out just two of very nice works, one from the Penn State, another from LSU, on how to capture these effects in CMB, effects on anomaly. And one is a theoretical work, which I did with my postdoc, in which we were trying to understand the deeper relationship between these two main approaches. So what is the motivation for this part? We have seen that the homogeneity assumption allowed us to understand the cosmological models as systems with finite degrees of freedom, but the physical universe is not exactly homogeneous. And we know that astronomical observations show that small inhomogeneities in the very early universe serve as the seeds of the large-scale structure. As I discussed earlier, these inhomogeneities arise from quantum fluctuations of the scalar fields in the very early universe. And the quantum fluctuations of the inflaton, they actually freeze out on exiting the horizon. And then when they re-enter, they generate classical density perturbations, and then they are mapped on into cosmic microwave background, which then provides a very important tool, not only to understand inflationary models, but any modifications to pre-inflation coming from quantum geometry. So while the inflationary paradigm, it predicts remarkable compatibility with observations, there are still some anomalies which remain to be understood in standard model of cosmology with inflation. And the goal of some of the practitioners of loop quantum cosmology who are working in this area is to understand how do we use these quantum geometric effects to explain these anomalies, especially, for example, for the largest angular scales. This part of the talk is quite technical. So I apologize if I'll have to skip some parts or go fast on some parts. But if you wish, like I can send you these slides later on. And these slides, I can assure you these slides will be helpful for any young student to really see what are the operational tools to actually start doing perturbations and so on. My goal will be basically, after giving some more introduction, to focus on Langlois paper. And even Langlois doesn't go into these details, which I'm going to talk about, so that any student who picks up this paper, which is very dense, couples of with these slides, can easily follow out. Yes, this is what exactly was done. This is the broad picture. This is how I proceed to do perturbations in loop quantum cosmology.
Param, this is Abhay. Just a quick comment.
Yes.
The organizers have allowed us, I mean, I have the facilitated to put the slides on the website. So therefore, you don't have to go into all the details. You can focus on the conceptual things, and then the students can look at the slides at the end afterwards.
Sure. Thank you. Thank you. I think that would be great. So at some point, I would just maybe like Jurek, you can mention how much time I have right now so that I can already.
A little more than 35 minutes.
Okay. So at some point, I would probably skip some part of the derivation, and that is clearly explained in slides, what you have to do from one equation to another, and you'll be able to follow. But I'll be focusing on some of the introduction and then some of the later part. Okay. So why we want to do this? So if you remember, I was showing you this picture earlier, some part of it, but you can complete that picture using effective dynamics of loop quantum cosmology. And this was again the co-moving Hubble radius plotted versus the scale factor. I'm doing the same exercise now. Earlier there was inflation, radiation, dust. Now if you couple that to loop quantum cosmology, you can go back. You can go to the pre-inflationary phase, and then you see that actually this is where the Hubble rate becomes 0. So this is blowing up here. And then it matches on to something like this. A sub on means this is where the inflation starts in loop quantum cosmology after the bounce. AS means this is where the superinflation starts. And it ends. And then there is a phase of neither inflation nor superinflation, and then inflation starts again. So superinflation, no superinflation, inflation, and so on. The primordial seeds or the physical wavelengths which were here, they were exiting the horizon and they were entering before the CMB was, or just when the CMB was being generated. These seeds now go past, and you can track them past, and they are now in the bounce regime here. Then they enter into, then they go out, and then they re-enter, and then they go out, and then they re-enter. And this is just a bounce. But if you're looking beyond the bounce, contracting branch would have a very similar trajectory like this. So they will be coming from the contracting branch, entering the bounce regime, exiting the bounce regime, entering inflation, exiting inflation, and then entering again. So this entry, exit, multiple times, this is our opportunity to encode the quantum gravity effects on these seeds and then to see whether we can get the CMB. So the modes can cross in and out of the horizon even before the inflation starts. There can be departures from the vacuum state, which is generally taken to be the Bunch-Davies vacuum or the primordial power spectrum. So the nature of bounce obviously depends on regularization. This is loop quantum cosmology. This is similar, will be MLQC2, but MLQC1 will be very different. But again, this again is an opportunity for us, this difference from inflation and the difference between different models. How will these primordial seeds travel, and how will the quantum geometry effects will be captured on these primordial seeds? This is our opportunity to learn how to encode quantum geometry and then to distinguish different quantum ambiguities on all this. And later on, I will show you how it happens. Okay. So something about CMB anomalies, and this is very, very brief. And I have to apologize. I'm not an expert on CMB anomalies. Abhayash Tekar is a much bigger expert on this in the audience, and also some of the cosmology students. So if you have questions, I can try to answer. If I'm unable to answer, I will redirect to them. But just to bring us all on the same page, there are 4 kinds of anomalies which have been studied. There is a power suppression anomaly, so basically what is plotted here is a power which is in the 2-point correlation of that CMB map I showed you, versus the multiple moments when you are writing that power in terms of the spherical harmonics, which are these L's. These are the large angular modes. And you can see here, these red dots, these are the Planck observation. And this green dot is basically the GR fit with, I think, with one of the favorite inflationary potentials. Or basically different infiltration potentials. And you can see here that the GR fit, or the lambda CDM, which is called, is this green curve. And you can see there is a lot of power suppression here. And this is a lack of 2-point correlations at the large angular scales or low multipoles in comparison to the lambda CDM model. That's a power suppression anomaly. And this is one of our windows to explain, can quantum gravity explain this anomaly? There is also dipolar modulation anomaly, which is the evidence in the observations of, which is a scale-dependent dipolar modulation between the multipoles of L and L plus 1. So between L, we pick some L and L plus 1, and there is a modulation anomaly which depends on whether you do it here or whether you do it here, and so on. There is also parity anomaly. The lambda CDM predicts parity neutrality when you're looking at different angular scales, but there is an excess power of all multipoles for large angular scales. If you look at 2 here, this is lower. Then if you look at the even ones, they are lower, but then for the odd multipoles, there is an excess power, as you can see from here. There is also lensing anomaly, which essentially means that the CMB, as it is projected out, and we see the CMB back in the sky, it undergoes lensing by intervening matter. But there are certain incompatibilities which have been found with lambda CDM model, and some work recently has been to understand these lensing anomalies in loop quantum cosmology. So these 4 anomalies are the primary main anomalies which people have tried to address using loop quantum cosmology. Let me put you a brief overview of the main approaches, and I'm not going to go into the details of the main approaches because that itself is an ocean to cross, and I will not be able to do a fair job to any one of the approaches and so on. So I will try to give you a third-party perspective. I'm not aligned with either of the approaches politically. Being politically neutral, I've tried to understand these 2 approaches, and this is what is my summary, and hopefully my collaborator's summary. But I do not blame them if they do not still agree with me. Okay, so what is a brief overview of the main approaches? So I'm not going to talk about other approaches, which, for example, are the deformed algebra and also another approach, which is separate universe approach. Not because they are not interesting, but lack of time. So I'm just going to focus on 2 main approaches, which are the dress metric approach and the hybrid approach. So the pragmatic strategy which both of the approaches follow is to consider a Fock quantized perturbations over a loop quantized background. There are 2 main approaches, one which was developed in Penn State and simultaneously another approach which was developed in Madrid. Both the approaches at a fundamental level, at a practical level, they result in modifications to a fundamental equation, which is called as a Mukhanov-Sasaki equation. They follow different routes, but eventually the task is you have a Mukhanov-Sasaki equation, and what are the modifications in that Mukhanov-Sasaki equation? The classical theory, if you look at before the quantum theory is applied, the classical theory on which the dress metric approach is based on Langlois' beautiful work on Hamiltonian method for perturbations. The classical theory on which the hybrid approach is based on Halliwell and Hawking's work on cosmological perturbations, which was in 1985. In classical theory, both approaches lead to the same Hamiltonian up to the 2nd order in perturbations at the effective space-time level. Now, if you go beyond classical theory, as far as I understand, the difference in phenomenological predictions between the 2 approaches in the Planck regime, it can be traced back to the quantum ambiguities. I will touch on that later on. I will try to show you the way we have tried to understand the relationship between these approaches and so on. The reason why I spent a lot of time on this is because both of these are very rigorous approaches, and it will be nice to see if there is any relation between them and in what sense they are really different and so on. That was my academic goal. Now, brief overview of results. There are significant advances in the last few years to connect quantum geometry effects with precision CMB observations. The main result is, if you do not choose some particular types of special states, the main result is that there is an agreement. Whatever approach you take, dress metric approach or hybrid approach, whatever regularization you take, the main result is that there is a beautiful agreement with observations at ultraviolet scales with the CMB. What does it mean? What it means is that if you look at these scales, basically, these are, I'm not showing the primordial spectrum. So, but basically like going from here, so on, there is a beautiful agreement. In the intermediate regime and the infrared regime, yes, there is a power amplification. But then you can also choose very special states, some space states which are very well motivated, for example, using the Weil conjecture of Penrose. Special choice of vacuum states can potentially alleviate the power suppression and lensing anomalies. And this is a very beautiful work which Ashtekar and Gupta and collaborators have done in the last few years. Similarly, Agulo and collaborators have shown that if you go beyond some of these states and look at non-Gaussianities, then they can also play a very important role in alleviating anomalies, including the parity asymmetry anomaly. Madrid group has also looked at other vacuum choices, such as non-oscillatory vacuum states of low energy, which can also alleviate anomaly. Then these were all in standard loop quantum cosmology, more or less. But like with my collaborators, we have been looking at modified versions of loop quantum cosmology, which I discussed, MLQC1 and MLQC2. And our conjecture is that as standard loop quantum cosmology leave the imprints, they can also probably leave imprints in cosmic microwave background. Okay, Jurek, so can you tell me the time? How much time is left?
27 minutes.
Okay, so I think I'll spend probably some time on setting up the framework and skip the main calculations and then come to the main flesh of the perturbations later on. So I'm going to go back now to Langlois paper. And I think like if one wants to start, any student who wants to start doing perturbations in loop quantum cosmology or something aligned like that, this is a beautiful reference, and just work it out, this paper, and then you are ready to do perturbations in loop quantum cosmology. So the main idea is that we let us start with a massive scalar field like an inflaton, which is minimally coupled in GR, which has an action which is given by this. Here kappa is going to be 8 pi g throughout this part of the slide now. In the ADM formalism, we are going to use a lapse function, and we have a shift vector, and we use this lapse and shift vector to foliate the 4-dimensional space-time into 3-dimensional space-like hypersurfaces. The induced metric on the spatial hypersurfaces I'm going to denote by gamma ij, and its conjugate momentum is pi ij. Similarly, you can write down for the phase space for matter, again, inflaton, phi and pi phi, which satisfy these Poisson bracket relationships. This is in full glory, full inhomogeneity, and so on. Now you can write down the action in terms of the canonical variables, and since it does not contain any time derivatives of lapse and shift, they are like Lagrange multipliers. And the extremization of this action with respect to the lapse results in the Hamiltonian constraint, where gamma is determinant of gamma ij, pi is pi ii. That is why I got rid of 8 pi g, and I'm using kappa everywhere. And the variation of this action with respect to the arbitrary shift vector leads to a spatial diffeomorphism constraint. So this is the Hamiltonian constraint, and equation 35 is a diffeomorphism constraint. The dynamical evolution of the background and perturbations is determined by this Hamiltonian now, which now depends on gamma ij phi as the configuration variables, and pi ij and pi phi, given as integral d cube x, lapse times the Hamiltonian constraint, and shift times the spatial diffeomorphism constraint. The physical solutions lie on the constraint phase space, which satisfy h equal to 0 and hi equal to 0. And since the Hamiltonian is composed completely of these constraints, which are first class, the Hamiltonian evolution preserves constraint dynamics. You can write down, the rest of it is just plain algebra and calculus. You have to write down the Hamilton's equations of motion for matter, phi dot and p phi. Similarly, equations of motion for gravity, gamma ij dot and pi a dot. Long exercise, but you can easily do it in few pages. And here dA is a covariant derivative on spatial hypersurfaces. We are not going into the details of this. I'm just going to flash some of the equations. Now let's go back to the cosmological background and let's do it slightly more rigorously. So the space-time metric, as I showed you earlier, now I want to write it in this particular form of this alpha, which is given like this, and later on it will be like e to the power alpha will be a. So log of a will be alpha. This is the metric, n is the lapse. The background variables I'm going to denote by gamma bar ij and pi bar ij. And then you can write down them in terms of alphas and pi alphas, where pi alpha can be written in terms of alpha dot using Hamilton's equation. And then you can relate them in terms of the scale factor and its momentum which satisfy these Poisson brackets, which have this 1 over V naught in them. So that is why the reason why this V naught appears in this Poisson bracket now is because my P phi is different from pi phi, which I'm calling now, just to be consistent with Langlois convention. And there is a V naught which will appear. In the cosmological background, in the homogeneous background, the spatial diffeomorphism constraint is satisfied. It vanishes because of the symmetries. And the only non-trivial constraint is the Hamiltonian constraint, which now in terms of pi a's and pi phi is given by this. And the zeroth order Hamiltonian for the background, x0 part is just this part up here, this equation 48. You can again look at the Hamilton's equations of this zeroth order Hamiltonian, the dynamical evolution. And then it turns out that if you take laps equal to 1, these Hamilton's equations immediately lead you to the Friedmann equation, the Raychaudhuri equation, the Klein-Gordon equation, which essentially is the conservation law. So we have completed the square. I've just recasted in terms of these new variables which are useful. And then I've shown from the Hamiltonian dynamics that you can get back to this modified, this Friedmann, Raychaudhuri, and Klein-Gordon equation. Now we do the linear perturbations. To do the linear perturbations, we consider linear perturbations of the spatial metric and its canonical momentum in this particular form, gamma ij as gamma bar ij plus delta gamma ij, pi aj is pi bar ij, delta pi ij, and similarly for phi and pi phi, we go to a Fourier space and we keep in mind our normalization conditions and the reality of these perturbations. Then in the Fourier space, the Poisson brackets look like this. I'm going extremely fast, but you can look at the slides later on. And these conditions will be, if you want to relate the Langlois paper with, let us say, what Ashtaker, Agulo, Nelson paper was, these slides will be very useful to make a map from one to another. Then you can define an orthogonal basis in this Fourier space for the scalar vector tensor decomposition. And I won't go into the details of that, like how to do this scalar vector tensor decomposition. But the idea is that you can define these these matrices, which are labeled by aij's for 1, 2, 3, 4, 5, 6, which can relate to the scalar vector and tensor perturbations, scalar vector and tensor modes in very specific ways, which I'm now showing here. What will be the scalar mode? How will you write the vector mode? And how will you write the tensor mode? And how will you similarly write the momentas? As you have written the metric fluctuations, how will you write the momentas in the scalar vector tensor modes and so on?
Excuse me, we have a question.
Yes.
I have a small question about the Fourier decomposition that you did. I wanted to ask if it is possible to do this decomposition in terms of the e to the I kx modes on all backgrounds.
What do you mean? No, I'm just focusing on the, yes, that's a good question. I'm just focusing on spatially flat background here.
Okay, so if I choose a different background, I might not be able to do that decomposition, is it?
Yes, thank you so much. Like this Fourier decomposition is for spatially flat k equal to 0 FLRW only. Even if you take k equal to 1, it becomes slightly complicated. It's doable, but it's not going to follow this. Similar thing can be done, but it's much more complicated. So I won't go into the details of that.
Okay, thank you.
Okay, good. So far we have written down this metric perturbations, etc., in terms of the Fourier modes. Then we have to attack each of the constraint. We did the background one. Now we have to do the linearized spatial diffeo constraint. We have to do the linearized Hamiltonian constraint, and then we go to the second order Hamiltonian constraint and so on. So this is the linearized spatial diffeo constraint. I write it in the Fourier space, and then it leads to three constraints because of its vanishing. Each of these three constraints being first class, they require a gauge fixing condition, and then it eliminates 2 degrees of freedom in the phase space. The first two constraints, these first two constraints, they fix the vector perturbation, so that is why we are not going to talk about them. And that is why Langlois says they can be gauged away. He densely mentions this at some point. I'm also filling in some steps you will need for the Langlois paper. And the third one, along with this one, eliminates the 4 degrees of freedom. So starting from gamma ij, where we had a symmetric matrix and 10 degrees of freedom in scalar and vector subspaces, one is left only with 2 degrees of freedom in the phase space. and thanks to the linearized spatial diffeomorphism constraint. Now, you can make a choice, and this is a topic which is very interesting. You can make a choice always in the perturbation theory, whether you want to work with the gauge invariant treatment, which means that you retain all degrees of freedom throughout the calculation and express the final result in the phase space using gauge invariant variables, such as a Mukhanov-Sasaki variable, which is used, which is generally written in terms of the fluctuation of the field plus all these components and so on. So either you do the gauge invariant treatment or you work in a specific gauge. For example, Langlois, in the middle of his paper, he switches to a spatially flat gauge in which Q, which is this Mukhanov-Sasaki variable, is delta phi. And then you can identify in the spatially flat gauge. If you look at the spatially flat, I won't go into the details of the gauges and so on. I'll briefly mention. Spatially flat gauge essentially means that the intrinsic curvature is just zero everywhere in this particular gauge choice for the perturbation. And if intrinsic curvature is zero, then I will be able to show that this term is zero and this Q is delta phi. So what happens is that in specific gauges, gauge invariant variables have natural interpretation. For example, there is another famous gauge which is called as a longitudinal gauge or zero shear gauge, which amounts to an isotropic threading of spacetime and a shear-free slicing in ADM formulation, which was given by Bardeen. And here the Bardeen variables become natural choice because they directly capture the amplitude of metric perturbations. So different gauge fixing conditions have natural physical interpretations and so on. So one should not be too much carried away either by this or this. And I will just emphasize what Bardeen has emphasized, that the physical relevance of gauge invariant variables is tied to gauge fixing conditions. So this is a nice, important topic, long topic. Maybe we can discuss later on at some point. It's not possible to discuss it right now. Now, the spatial diffeomorphism constraint with the spatially, if you do with the spatially flat gauge, then the analysis becomes simpler. You can then take gamma 1 and gamma 2 to be 0, and then you can write down this equation, which is just a linearly spatially flat diffeomorphism constraint. And in the spatially flat gauge, and I'm now coming to the spatially flat gauge only, one can express this pi 1s and pi 2 also in terms of delta phi and delta pi phi. So the magic of the spatially flat gauge is that you can go to delta phi and delta pi phi immediately, and then the calculation becomes much simpler for linear spatially diffeomorphism constraint, and also like the Hamiltonian and so on. Similarly, you can do the Hamiltonian constraint analysis at the linear level, and I'm only looking, and this only consists of the scalar modes, and it again simplifies a lot in the spatially flat gauge, giving you this equation 77, and then we'll be using the linearized spatial diffeomorphism constraint and linearized first order Hamiltonian in the spatially flat gauge later on. Now let's come to the second order Hamiltonian, and I'm pretty sure, like, since I'm very much far ahead of time, I'm just going to flash the slides that you can look at this second order Hamiltonian in a similar way. It's a long calculation, even in spatially flat gauge, but you can eventually obtain a Hamiltonian using the linearized Hamiltonian, using the linearized spatially diffeomorphism constraint to eliminate certain things, and then you will get certain cross terms up here, as in the Langlois paper, and then you can write them down in this beautiful form in the end. This is what Langlois achieves as a second order Hamiltonian after a lot of calculation, where this omega q square is some potential, and I'm calling this k as the wave mode, the momentum, which is inversely proportional to lambda, and the k physical, which is this related to k by through this a. Then this q is the Mukhanov-Sasaki variable q. This pq is the momentum of this q, and this q and pq, they satisfy this Poisson bracket through the Hamiltonian, this Hamiltonian flow, and they have these Hamilton's equations. From these Hamilton's equations, you can find out the Mukhanov-Sasaki equation, and in the effective description of LQC, this becomes at a practical level. So if you don't go through the quantum theory of the rest or the hybrid approach, if you just stare at this equation, what you're going to do is you have these effective backgrounds of LQC, and then you are going to play these background variables in this Mukhanov-Sasaki equation, and then you can substitute those background quantities from the polymerized background into this Mukhanov-Sasaki equation. So I know like I was probably not very, very coherent so far. So let me just explain. We have obtained this Mukhanov-Sasaki equation, which looks like a Klein-Gordon equation, from this Hamiltonian, which we have obtained from, at some point using the spatially flat gauge, casting these variables in delta phi, delta p phi. And then for that, we have used somewhere linearized spatial diffeomorphism constraint and linearized Hamiltonian constraint. And you may think, well, this looks like gauge fixed now, everything. The answer is no, it's not gauge fixed. Because the moment I make a choice from delta phi to q's, I'm back. In the final answer here, equation 82, is exactly the same answer which you would obtain from the gauge invariant choices. This was just a shortcut to obtain 82, 83. This is still completely compatible in the gauge invariant way. So in a way, like I just took a shortcut by doing some gauge fixing in the middle of the calculation. That is what Langlois does. But the final result is in terms of the gauge invariant variables, Q and its conjugate PQ. Now, you can also rewrite this equation. So Jurek, how much time I have?
12 minutes.
Okay, so you can rewrite this equation in this particular form, this omega q, which is there in terms of these background variables. And this is all so far in the classical theory. You can also repeat the calculation for tensor modes, which is slightly easier because they are not constrained by the linearized constraint. These are naturally gauge invariant. And it follows a very similar calculation of the scalar perturbations. You'll get this Hamiltonian at the second order, and you'll get a similar equation from the Hamilton's equation. Then in the background equations, how do we encode? How do different approaches encode different things? And here, like, it is useful to understand what is the concept of a mass function or an effective mass function. The perturbation of the spatial, it turns out that the perturbation of the spatial curvature, if you work in a different gauge, which is called a co-moving gauge, is a curvature perturbation, which is given by this curly R, which is given by nu by Z. This nu should not be confused by the volume eigenvalues in the previous part of the talk. This nu is also a Mukhanov-Sasaki variable, which is related to this capital Q through this scale factor A. This co-moving curvature perturbation, which is conserved across the horizon, is related to this Mukhanov-Sasaki variable nu through this, divided by Z, where this Z is given by this A phi dot by H. In terms of this nu, you can also obtain from this previous equation 86, this new Mukhanov-Sasaki equation. And these terms are in some sense very tempting to be identified through some sort, like a Klein-Gordon equation with a mass square term, which some of the cosmologists or even loop quantum cosmology people do, to write it as a mass square term, which is omega q square minus A double prime by A, where the prime is now the derivative with respect to the conformal time. Then the analysis is that, yes, you can write down these mass functions in different ways. You could, for example, like instead of doing this analysis in terms of Q, I could have said, I don't want to follow Langlois' approach. I don't want to work with Q. I want to actually work with nu, because that is directly related to the curvature perturbation. And I can just write down that in the same form. And then it turns out that you can do that, and you will obtain a different mass function. But it turns out that those two mass functions, they are essentially the same on the space of physical solutions in GR. It should not matter, right? In the classical perturbation theory, it should not matter whether you work with Q, or whether you work with nu, whether you work with one gauge or another gauge. The mass functions should not matter in the space of physical solutions, and one can show that the mass functions computed through one method or through the Q method or the nu method, they just give you something which vanishes completely on the space of physical solutions. They are completely equivalent. Now, you can ask the same question for gauges. What one can show is for the classical, till you are in the classical GR, these mass functions really are absolutely equivalent to each other on the physical space of solutions. But you see, like what happens is that this is actually not going to be true at the effective space-time level in loop quantum cosmology. And that is where the difference comes in the two approaches of doing perturbations, because one approach follows one trajectory, other approach follows the other trajectory. And then there is a difference where you quantize what, where do you bring in which input of loop quantum gravity. And that is why they do not, this, if the effective mass function in the effective description would not vanish on the space of physical solution. So I'm going to skip this part, and I'm going to skip this part also, but I'm just going to come to this part, that if you look in the effective description, if you do the same analysis, you find this term up here, which is rho by rho c. And this term does not vanish. Neither it vanishes at the bounds. This doesn't vanish anywhere in the Planck regime. Yes, it goes to 0 if you are away from the Planck regime, because then this rho becomes much smaller than this bounds density, which is rho c. It becomes 0. If you go to the classical GR, then the two approaches agree. But if you are in the Planck regime, there will be difference of the mass function. The main thing is that the different approaches to include quantum geometric effects, if they bring them at different steps, they leave a trace. And that is what becomes an opportunity to not only look at different approaches, but also to look at underlying quantization ambiguities. If different approaches are leaving signatures, one can be very optimistic that quantization ambiguities will also leave a signature, and the mass functions would not vanish in the effective dynamics. This does not go to 0 on the space of physical solutions of the background dynamics in LQC. So can there be quantum geometric signatures in CMB? And this is where a lot of work has been done. And underlying quantum geometric signatures in LQC, like as I mentioned to you, that lead us from a departure from the vacuum state. And given an inflationary potential and suitable initial conditions, there can exist an observational window which can potentially lead to observer imprint of pre-inflationary state. And this was a beautiful work by Ashtaker, Gulo, and Nelson, where they showed that this phenomena, which was earlier discovered by Parker and Fulling and other people, if the physical wavelength of the mode experience a quantum geometry scale, then this physical wavelength, when it is going on this quantum geometry, then there can be a window in the inflationary regime where, yes, there can be signatures of loop quantum cosmology. And again, like I won't be able to go into the details here, but this is essentially telling students like how to choose that window. And I've explained that in great detail, how to choose that observational window and so on, and how you have to fix that window. And you can go through these slides, given your favorite inflationary model, when does a bounce occur? How can you really fine tune this window or change this window? And I just want to show it here, how you can change this window. So basically the idea is that there is a minimum wave number you can see, and there is a quantum geometric wave number which experiences the quantum geometry effects. And I'm plotting this power spectrum versus the wave number divided by the pivot mode of the wave number. And so this is the ultraviolet regime I was talking about earlier. And these points are, let us say, from the observations. The brown points are the observational points. The red curve is, let us say, from standard LQC. I don't remember whether it was which approach, but both approaches give very similar answers, even in this regime here. And the idea is that, yes, you can choose this blue line shows the window which has been chosen where whatever happens in this regime, which is a departure from GR, will be captured in this primordial power spectrum, and then you will be able to see in the angular power spectrum. So this is the primordial power spectrum, which is the square root of the Mukhanov-Sasaki. This is a power, essentially, roughly speaking, square of the Mukhanov-Sasaki variable in the Fourier space divided by Z, which I was mentioning. What is that Z? The main idea is that take your favorite inflationary potential, choose your approach, do the perturbations the way, for example, Langlois does, plug in the quantum geometric corrections, and then you can very carefully choose a particular window in which, yes, you can be promised there will be signatures, and those signatures I'm showing in this example. And I'm actually borrowing a slide from a talk which my student is going to give on Tuesday, in which you can repeat this exercise for whichever approach you want, whether you like dressed or hybrid approach, whichever potential you want, whichever regularization you want, standard LQC, MLQC1, MLQC2, whichever initial state you want. So I'm plotting essentially the power versus the multipole moment here. The green curve is lambda CDM. The dots are the experimental dots along with the error bars here. And the red curve is loop quantum cosmology for fourth order adiabatic states. MLQC1, I think this is the hybrid approach, which allows then the fourth order adiabatic states, MLQC2, fourth order adiabatic states, and so on. And as you can see, the quantized, if you choose a different regularization, there is a different result. These are not some special states, these are just pure fourth order adiabatic states. There's a different result. And you can see here the MLQC2 is actually giving power enhancement instead of power suppression. So we can probably looking at this figure, we can say, well, MLQC2 looks unfavorable. Similarly, you can look at MLQC1. And similarly, you can look at LQC. And you can see that LQC has a beautiful match throughout with the lambda CDM. And it is giving here some power enhancement, but this is for adiabatic states. If you choose special states, which are very well motivated, like what Ashtekar and Gupta, or non-Gaussianities like Gulo and Srinath have done, then there is a power suppression, which is possible. And then this can be explained. So since I have not done that work, and I generated these plots in my own collaboration, so I thought I should show this plot also as an advertisement for my students' talk. But this is not the final answer. If you choose the state, if you take second order states, then the blue and red curves will flip. So the main message is you can do this Mukhanov-Sasaki analysis. You can include quantum geometric perturbations. You can study different cosmological LQC and its variants. And you can also choose different initial states. And the answers here will not only depend on the regularization, will also depend on the initial states. So there is a huge frontier which can be explored beyond standard LQC with different initial states. And then you can look at the predictions of CMB into this regime. So essentially, like this is where you can clearly see that different quantum cosmological models are giving different predictions compared to lambda CDM for a specific choice of initial states. So I'll just summarize part B now. I'm sorry, like I had to rush a lot. I really wish I had 3 hours for this, and I could have gone through each step very carefully. Main steps, main answers, quantum geometric effects in loop quantum cosmology have been extensively explored in CMB, starting from 2012, when the dress metric approach was formed, and even before, earlier works have been there. Dressed and hybrid approaches, they use Fock quantized fluctuations over loop quantized background at an effective level. And I'm saying at a pure physics, practically, like cosmologist level. I'm not talking about the quantum theories here. And they have their own beautiful properties and many nuances, which I've not covered. At an effective level, Mukhanov-Sasaki equation plays an important role, where background quantities from LQC are imported. Power spectrum depends on the choice of states. If you choose adiabatic states or special states, the answer will be different. And for certain choices, it is certainly possible to potentially explain CMB anomalies in loop quantum cosmology. And a lot of work has been done on that by Penn State, Madrid group, Agulos group in LSU, and so on. Different regularizations can potentially leave different signatures. And this is something which is developing, which is new. Novel results are on here. Like you can really distinguish LQC from MLQC1 and so on in the angular power spectrum, as you can see here. And again, this is only for one initial state. My student will show you many more interesting results on Tuesday. And the open question, which is, again, my open question, like the way I understand the picture so far, is that our real challenge is to identify the unique observable signatures of loop quantum cosmology or MLQC1 or MLQC2 or any other cosmological sector of loop quantum gravity, which are not mimicked in GR or modified theories of GR or modified gravity models and so on. I think our main challenge is not only robustness, but also uniqueness. And if we can find a unique signature, which is really the true smoking gun coming from loop quantum gravity, I think that will be a huge victory for this entire field. After that, we should not care whether the model is true or model does not hold up to observations. We already have made huge progress, a lot of progress on linking quantum geometric effects to CMB. I think there were many challenges there that has been achieved. I think the next target should be to find out that unique signature. And I apologize if I'm already missing some unique signature, which is already there. And maybe the experts in the audience can correct me on that. But I think like going 5 years down the line, this will be the real thing which will be asked from our field, and we have to work on that. With that, I will pause and take any questions.
Let us think. So we don't have much time for questions. But
thank you for your talk. I don't know if you could please tell us a little bit. So you mentioned this parity anomaly on odd multipoles. Could you tell us if and how loop quantum gravity concepts are used to potentially explain this phenomenon?
I think that's a very good question, but that's also a very difficult question for me to answer it very, very briefly. I think if I'm, and maybe like Abhay is there and Abhay can correct me if I'm wrong. One of the ideas was that if one chooses certain types of states which are motivated from this Penrose conjecture, then one can explain there is a power suppression, and then these papers were able to show that both the power suppression anomaly and the lensing anomaly, they can be resolved. This was more a property of the state. Everything else, or the Mukhanov-Sasaki equation and so on, that remains true as it is. The where to include terms and so on. But I'm not sure if I can answer really like how that choice of state really solves this anomaly. I know like how it works, but I don't have a deeper intuition on why that particular choice of state works and why not adiabatic fourth order or so on. Maybe Abhay, like if you can help me on this.
I really think that it's a long question, it's a long answer, and we don't have enough time, but I'll be happy to explain, to Francesca or anybody else is interested afterwards. I think that
thank you,
we have the afternoon thing. But since I have a mic, I just want to say one thing, that thank you for advertising this Langlois' work. But when we're doing this perturbation theory, actually Nelson found that there are several important typos in the paper. And then he also wrote to Langlois. Langlois completely agreed that with the thing. But then he had lost his tech files, so you could not submit an erratum. So I think along with your talk, I think we should perhaps post this Nelson's corrected file of Langlois' perturbations, so that it will save a lot of time to the students who are trying to understand the perturbation theory.
Yes, I completely agree. And I also, actually, like when I was working on Langlois' papers with my postdoc, Baofi Lee, who will be also giving a talk, I think on Friday, has one of the plenary talks. We also found lots of typos, but I did not have courage to write to David Langlois, so I just fixed those typos in my notes, and we just worked out various things ourselves. But thank you so much. I think if Nelson really had a PostScript version of that, that would be really useful for the students. Also, like in some of the earlier works with Baofi and myself, if you look at the earlier papers in the last 3 years, we also have filled various steps of Langlois' work. So where some of the typos are fixed. I don't think like we have written down all the notes, like they're like this big, thick handwritten notes. So I have never checked them so far. But thank you, Abhay. Like I think it will be great if Nelson's file can also be posted.
So let us thank the speaker again.
Thank you, everyone. Thank you. I'll hope to see you soon.